So, hello everyone. I'm Arthur O'Dwyer, and I am here to tell you about Dynamic Cast from scratch, which you can't see because it's on the first slide, and I already went past that one. And I'm too scared to go back, because I don't want it to crash on me. But I'm going to tell you all about Dynamic Cast, about what it is, what it does, a little bit about how it's implemented, mostly about how it should be implemented. And I'm going to show how it should be implemented is better than how it is implemented. And I hope that there's someone in this audience who owns a Dynamic Cast implementation. That would be awesome. Come talk to me afterward. All right, so in part one, I'm going to tell you what it does. And in part two, I'm going to tell you, well, in part one, I'm going to tell you the background, what is polymorphism, and what are all the different toys that we have to play with. In part two, I'm going to tell you what Dynamic Cast does with those toys, how we implement it, and I'm going to show you my implementation. All right, quick recap. Polymorphism, classical object-oriented polymorphism. We have a class animal. An animal has some legs, and it has a couple of virtual methods. The virtual methods are basically function pointers held in a vtable, and the animal object instance has as its first member, usually, in the Linux ABI. I'll be talking a lot about the Itanium ABI, about the ABI that's used on OS X and on Linux. For Windows, this is largely the same with some differences around virtual bases. I will mostly not be talking about Windows. Be aware. All right, so we have a vpointer in the animal instance. And then we have cat. A cat is an animal. Cat inherits from animal, publicly. And a cat has all the stuff an animal has, and it also has a number of tails. And it can override one of the virtual methods of the base class animal. So when an animal in general speaks, it says hi. When a cat speaks, it says ouch. And when a cat speaks and it says ouch, it also knows about all of the data held in the cat, as well as all the data held in the animal, right? All right, and the way that we implement that is that the cat looks just like an animal. It has a vpointer in the legs, and then it has the extra stuff, the tails, and its vtable, that pointed to by the vpointer, also looks physically just like the vtable for an animal. It's got the speak method, and it's got the destructor in that order at those offsets. And that's important, because that means when we have a pointer to a cat, we can treat it like it was a pointer to an animal, and we'll get the right physical behavior. All right, right. For example, if I have a pointer to an animal, let's say A, and I call A arrow speak, what that does physically in the assembly is go get the thing at offset 0 from RTTI, that would be the v pointer, follow it, and go get the first thing out of the vtable, that would be start RIX here, and call that. So if A actually is the address of a cat, I get cat speak. If it's the address of a base animal, I get animal speak. If it's the address of some other kind of animal, I get that animal speak method. All right. So there are several different graphical representations, ways we can represent this idea. One of them is just in speech. I like to say a cat is an animal. Right? Cat inherits from animal. A cat is an animal. We can also represent it graphically by drawing out the struct layout. This is a representation of what the compiler actually will generate as the struct layout for a cat. Notice that it has first the vpointer and the animal data at the start of the cat, and then it has the cat-specific data after that. This is what gives us this happy coincidence that the first part of a cat looks physically exactly like an animal and allows us to use an animal star to get into it. All right. And then also over here, I've got a graphical representation of a cat descending from an animal. And we'll see a lot more of that soon. Multiple inheritance. All right. Now we get to the dreaded diamond, and we just interestingly heard Titus Winters in the keynote just talking about a different kind of dreaded diamond. This is also a dreaded diamond. Here we have class animal, and it has a virtual destructor, because why not? And we have a cat is an animal, dog is an animal, and then we have a cat dog, which inherits from both cat and dog. Right? Notice the lack of virtual keywords here, right? Public animal, this is intentional. So graphically, we have something that looks like this. Here's the layout of a cat dog. Right? Cat dog has physically its first base and then its second base. And its first base is a cat, and the cat has a base that's an animal. And so that we've seen before. The cat has an animal. That all looks the same. But then after that, we also have the dog part. And the dog also has an animal, is an animal. And then we have the cat-dog specific data down at the bottom. All right. So now we have a question. Is a cat dog an animal? How many people think a cat dog is an animal? How many people think a cat dog is not an animal? All right. Well, I'm going to make you happy. It's not. A cat dog is not an animal. A cat dog is two animals. It's got two animal subobjects. It is not an animal. All right. Because if I were to point to this cat dog and say, "Mommy, can I have that animal?" She'd be like, "Which one do you mean?" Right? It's not one animal, it's two animals. When I point to the cat dog, I have no idea what animal I'm talking about. However, we can fix this. If we can give the cat dog just one animal subobject, then when I point to it and say, "I would like that animal," you know exactly which one I mean. And we do that with virtual inheritance. So in C++, we have the idea of virtual inheritance, where I can inherit by saying cat public virtual animal, dog public virtual animal. And now that animal base subobject sort of deduplicates itself. Whenever I have something that inherits from a cat or inherits from a dog, that animal virtual base sort of floats down to the bottom, even after the cat dog specific data. It just floats all the way down and deduplicates itself, so that now the cat's virtual base and the dog's virtual base have both combined. Right? And we have only one animal virtual base, and so we have a happy cat dog, because it only is one animal. All right, but now we've changed how a cat looks. Right? A cat used to look physically like an animal. So we could just we can have an animal star, it secretly points to a cat, and we could just treat it like it was an animal, because physically they were identical. Now we've changed how a cat looks. So now we have a problem. Now if I have, let's say, a cat star, and I want to access its number of legs, which is part of its animal virtual base, how do I actually get at that animal data anymore? I don't have a way to sort of offset into it, because there could be arbitrary stuff in between. There could be nothing in between. There could be a dog in between. I have no idea. So we have to distinguish between objects that are really just cats, like literally dynamically it is a cat, its actual type is cat, or objects that are cat but maybe more. Maybe it's a cat dog, maybe it's a tiger, I don't know. It's some kind of cat, but I don't know what else it might also be. Cat objects that are just literally just a cat, dynamically a cat, they have a fixed concrete layout. Cat objects that are maybe more have a fixed layout for all their base subobject pieces, but you have to do some work to figure out where those pieces are located. To generalize this away from cats into C++ classes, objects that are most derived have a fixed concrete layout dictated by their most derived type. And if I have an object of unknown dynamic type, it has a fixed layout for all its base subobject pieces, but to access a virtual base, you first have to figure out what is the most derived type of this object. That tells you its fixed concrete layout, and that tells you where its virtual bases are located. So how do we figure that out? How do we find out at runtime, given that I have a pointer to a cat, given that I have a pointer to an animal, how do I figure out its most derived type? I can't do that statically. I have to do that dynamically somehow at runtime. How do I do that? Well, we have a place for stuff that's determined dynamically at runtime. That place is the vtable. So, vtables. Vtables have two things going on in them, right? There's the schema of the vtable, of what stuff does it contain. It contains a pointer to my speak method, a pointer to my destructor. The v-pointer itself is located at offset 0. Those are sort of the schema of the vtable. They define the shape of the data. But then there's also the value of where does that v-pointer point, what actually is the behavior of the speak method, what actually is the behavior of the destructor. That's the data or the values in the vtable. The schema of the vtable is dictated by the object's static type. If I know I have an animal star, or I know I have a cat star, the animal star will always point to something that looks physically like an animal. It has all of the animal bits in known places. A cat star will point to something that has all the cat bits in known places. And then I have to go look at actually what are those bits. And those bits will be dictated by the object's most derived type, the dynamic type. So in this example, I have a cat star, and the fact that the cat object has a virtual base animal is dictated statically by the fact the object is a cat. Every cat has a virtual base animal, I just might not know where it is. So the presence of it is dictated statically, the actual location of it is dictated dynamically by the most derived type. And the place where all this stuff comes together is in the vtable. So we should assume that we can find our virtual base animal by querying our cat object's vtable. All right. This is how our memory layout looked on slide 4. Let's update it, hopefully. Let's see, this is not virtual inheritance. This was regular inheritance. Here's virtual inheritance. Our animal virtual base has floated down to the bottom of the cat. And now, because animal is also a polymorphic type, it also has a v-pointer, right? So we have a v-pointer for the cat and a v-pointer for the animal. And they both happen to point to two vtables whose data is controlled by cat. In fact, this isn't even quite right. We really have something more like this. This needs to be a vtable for the animal subobject of a cat, whereas that is a vtable for the cat object itself. And the difference is these little asterisks, these little red stars. Cat speak with a little asterisk is identical to cat speak, except that when you call this, you're calling it because you have a pointer to an animal. But cat speak, the actual method, expects a pointer to a cat as it's this pointer. And if I have a pointer to the animal there, maybe I should actually use my mouse. If I have a pointer to this animal, right, that's 16 bytes offset from the actual pointer to the cat that cat speak wants. So when I call cat speak with a little asterisk next to it, I actually need to first subtract 16 from my this pointer before I can dispatch to cat speak. And this is called a thunk, because that's the noise it makes. All right. So when in doubt, it's in the vtable. We're looking for something where its presence is statically determined. It definitely has one of these things, but we need to find out what it actually is. In this case, the thing we're looking for that we know it has, but we want to know what it is. We know it has a most derived type, but we'd like to know what is its most derived type. So anything where we know statically it's got one, we just want to know what it is going to live in the vtable, because the schema of the vtable is controlled by the static type, and the stuff in it is controlled by the dynamic type. And most derived type is a synonym for dynamic type. All right, so in our vtable, Nextdoor is having fun. You probably can't hear that in the video. There's all sorts of stuff going on over there. We have, so at offset 0, we have cat speak. At offset 8, we have cat destructor. But also at the negative offsets, we have room to put things. And so we're actually going to put things there in the Itanium ABI. What we're going to put at offset -1, we're going to put a pointer to the type info for the most derived type. This is super convenient. So now, even when I've got A, which is a pointer to an animal, if I want to know its type ID, so type ID of star A, what do? I follow the pointer to, and I get the vputter, and I follow that, and I subtract 8 from it, and I dereference it, and now I have type ID of cat. So type ID of star A is type ID of cat, which is true. It is, in fact, a cat. Somehow, the animal virtual base knew that this was a cat. And the reason it can know that is because this v-pointer is getting filled in by cat's constructor, and it's initializing it to point to the vtable for animal in cat, and not the vtable for animal in dog or animal anywhere else. All right. Getting at animal data, right? How do we get at the animal base object of a cat? So here we have a cat star, and I would like to know how many legs this cat has. So I can no longer just index and add 16 or add 24 to get down to how many legs this cat has, because it might be more. It might be a cat dog. It might be a tiger. And so what I have to do is I follow its v-pointer, and now I know statically that this is a cat. It's pointing to a vtable for a cat in something larger, possibly. And I know a cat has a virtual base of type animal. I know that it is present, I just want to know where it is. And so where do we put that? We put that in the vtable. Somewhere in the vtable, we also have, I kind of skipped over the most derived offset. Says that this object that I'm pointing to right here, this v-pointer, is actually at the beginning of the object. There's nothing before it. And even before that, I have the fact that my animal virtual base is at offset 16 in this most derived type. Remember, this v-pointer points to a vtable which is controlled by the dynamic type, by the most derived type, and it knows everything about this object by definition. Because it is the most derived type, it's the type that was actually constructed here. This is the object we actually have that we will actually destroy later, and so it knows everything about itself, such as where its virtual bases are located, and it can expose that through the vtable. So here I have a function that takes a cat and returns how many legs that cat has. You run this through the compiler, you run it through Godbolt, and you see that here's C is in RDI. We dereference it once. We dereference it again and subtract 24. That gets us our animal offset. We add that to our original this pointer. So v pointer plus 16 gets us legs, more or less, plus 8. Yeah, this address plus that 16 to get us the beginning of the animal, plus the 8, that's the offset of legs in animal, gets us the number of legs in this cat. So accessing a data member of a virtual base actually requires 3 dereferences, where if it were a non-virtual base, it would only require 1 dereference. And here's a little vtable layout recap. Again, this is the Itanium ABI. MSVC is much more complicated. Any questions so far? I'll do a little pause. Yeah.
I'm still a little fuzzy on, you talked about the like the animal speak and the cat speak, and why we have to store it twice. And it wasn't like really obvious to me why we only have to store it twice when we have virtual inheritance and not when we have like normal or multiple inheritance or something like that.
So the question was why, when we have the virtual inheritance, we have 2 v-putters pointing to different vtables. Sorry, here we go. 2 v-pointers pointing to different vtables with thunks. When we have non-virtual inheritance, we can somehow get away with only 1 v-putter, and it points only 1 vtable.
Specifically, why does the speak have to be listed in both?
Well, in this case, this up here is a base animal, and that's speak. And here we have a cat that also is an animal, and so it physically looks like an animal, but it actually speaks like a cat. And we can get away with this because we don't have to do any offset adjustment. There's no multiple inheritance going on here. In a sense, you could think of it as this is both cat speak and cat speak with a little red asterisk. It's just that the offset we're applying to this pointer is 0 in this case. So we can get away with just having the v-putter do double duty for both animal and for cat.
If you have multiple inheritance, though, you might need an offset, no?
If you have multiple inheritance, then you will not, if you're multiply inheriting from, let's say, cat, then you won't need an offset. We'll have something like this. Each animal has its own v-putter here because there are 2 animals. But the dog can share its v-putter with its animal. Cat can share its v-putter with its animal. So it works out. All right. So in the subtitle, which you didn't really see because I had it already at the outline when we started recording, the subtitle is 2 kinds of inheritance graphs. So I'm going to talk now about how I visualize complex class layout. When I decided that I was going to figure out how dynamic cast worked and then I was going to implement it myself, there were a lot of test cases involved in this, and a fair number of bug reports for that matter. And when figuring out what is it that dynamic cast was supposed to do in this instance, I found that I needed a way to take an auto-generated class hierarchy and put it on a whiteboard so that I could sort of trace through it myself and figure out what I expected to happen. And so this is the system I came up for whiteboarding complex class hierarchies. Does anyone think that whiteboarding complex class hierarchies will be a useful job skill for them? I'm just curious. We have a few tentative hands. All right. I was hoping it wouldn't be like everybody. That would be the sorry state of the industry. But I do hope this is useful for some people at least. All right. So what I do is I pick which class am I interested in diagramming. So in this case, I'm making the diagram for cat dog, and I put it at the very bottom of my little tree here. And then for each of its bases, I make another little circle, and I put the name of that class. So I have cat dog inherits from a cat, inherits from a dog. It has a cat subobject, and it has a dog subobject. And then for each of their bases, I make a little circle and I draw a line up there, right? A cat has an animal subobject, a dog has an animal subobject. Notice this is not virtual inheritance. Therefore, if I turn this sideways, it looks an awful lot like the diagrams we were drawing with the big boxes. It's just more compact. In the case that there's non-public inheritance, I'm going to draw a little dotted line instead of a solid line. So here, dog has a non-public animal base, and that will become relevant when we talk about dynamic cast. And then the last kind of inheritance we can have virtual inheritance. When you have virtual inheritance, remember your virtual bases sort of float down to the bottom and deduplicate themselves. So to indicate virtual inheritance, I put a big solid circle around the virtual base, and everyone points to that. As soon as there's a big solid circle around it, there's only going to be one big solid circled animal in any given diagram, because all the virtual bases are going to end up being shared. And here, quick question.
Virtual bases only deduplicate themselves with other virtual bases.
Virtual bases only deduplicate themselves with other virtual bases, yes. I could have one or more non-circled animals also in this diagram. All right. Notice also here that animal is a public virtual base of cat dog. There is a public path from cat dog to animal, but not from dog to animal, and that will also become relevant. All right, so lines indicate inheritance, nodes indicate subobjects, dotted lines indicate non-public inheritance, heavy circles indicate virtual inheritance. The root of the graph down at the bottom is the most derived object. There's always a single one of those because I'm interested in that class at the moment, not some other class. Some other class might have a graph that was just a subgraph of this graph, or it might have a graph that looked significantly different, mostly due to virtual bases. We also don't have a great way to indicate inheritance order here, such as cat dog inherited from public cat, comma, public dog, and not vice versa. That does affect the struct layout, of course, but inheritance order is not supposed to matter to dynamic cast. And if we had time for guessing games, I would not give you the solutions to these, but I decided in the interest of time, I'll just put here's some possible graphs, here are some impossible graphs. So these are all possible. Here's an example of Gaspar's point about having a virtual base L and a non-virtual base L in the same class layout. And over on the right-hand side, we have EFGH, where it's reasonable except that G has no business being in there. Where it's not part of H, we clearly don't care about it right now. G shouldn't be there, or something. Over here, U, the object at the root of this hierarchy, has been marked as a virtual base of what? That doesn't make sense. Over here, Z inherits from Y twice. That also doesn't make sense, not to mention both Ys are circled indicating their virtual bases, and there should only be one of it. And then this last one is a little more subtle here. We have X inherits from W and Y, Y inherits from W, W inherits from V. But in one case, W inherits from V publicly, in the other case, W inherits from V privately. But W is a class. Like it has to either inherit publicly or privately. It can't do both. That's not a thing. So that's also an impossible graph. Again, these are not like graphs you have to avoid or anything. I'm just pointing out by these conventions, These graphs make literally no sense. Those graphs are possible to get from C++ programs. And we can match these graphs to their code. I'll leave that up for the video, and I'm just going to go on. All right. Now we've gotten to a break. How am I doing on time? Not bad. So now I'm going to start actually talking about dynamic cast. We have now completely explained everything there is to know about classical polymorphism. And now I'm going to talk about what is dynamic cast and what does it do. Are there any questions about anything at this point? Cool. So what should dynamic cast do? Let's say I have this little function test, and all this does is it takes a pointer to an animal, and it says, I would like that cat, please. So it takes a pointer to an animal. So I'm at the pet shop here, and I point to this animal, and I say, I would like this cat, please. And the pet store owner says, okay, here, have this cat. Easy, because this cat is this animal. I point to this animal, and I say, I would like this cat, please. Now there's a problem, because this is not actually a cat. Right? So what dynamic cast to cat star is going to do in this case is going to give you back null. If I tried to cast it to dynamic cast cat reference of animal, it would throw bad cast. I'm going to stick with casting pointers here because pointers are nice, and I can just say this gives you null. And we can implement one behavior in terms of the other easily enough. Okay, so I have a pointer to this animal. I say, give me this cat, and it gives me null because this animal is not a cat. Now I have a pointer to this animal, and I say, give me this cat. Now in this case, this animal is a base object of a happy cat dog, which is a cat. Besides which, this animal is a base of a cat, so it says, sure, here, have this cat. Gives me a pointer to this cat. Let's go over here. Now I have a pointer to this animal, and I say, give me this cat. Everyone sees my pointer, I hope. I say, give me this cat. This animal is the base of a cat. Here you go, have cat. Now we get to a more interesting case. I point to this animal, and I say, Mommy, I would like this cat. I am clearly pointing to something that is a dog. But this dog is part of a cat dog, and the cat dog is a cat. Now, cat dog is not an animal. I'm pointing to this animal and saying, give me this cat, and the animal I'm pointing to is not a subobject of a cat, and in fact, the most derived object is not even an animal. I'm pointing to the animal, but it's not an animal. And I'm saying, give me this cat. And it says, okay, and it gives me this cat. Because I'm definitely pointing to an animal, right? And there's only one cat I could be talking about. So dynamic cast is defined in such a way that it will say, okay. It tries to make me happy. I will give you this cat. All right, now I point to this animal and I say, give me this cat. Now there's a problem. Now this animal is a base of two different cats, and it's not going to give me a cat. It says, just like before where we saw the cat dog was not an animal, now we have an animal which is not a cat. It's two cats. I know that's not what a Siamese cat is. All right. So ambiguous bases, right? We have an animal here which is two different cats, and I don't know which cat I want. It's ambiguous. Oh, question.
Yeah. In the first graph, if you dynamic cast that animal to cat, will the pointer value change?
If I dynamic cast this animal to cat, will the pointer value change in the sense of does it point to a different memory address? Well, it depends on how cat is defined. Given how we've been defining cat, no, a cat physically is an animal. Or I'm sorry, this is a virtual base. So I believe it will, but don't quote me on that. Just go try it. Question.
In the Siamese cat, if you change the path from virtual inheritance to regular inheritance,
Then we would have the angry cat dog.
well, not angry cat dog only has one.
Oh,
cat.
this would be a cat and the cat. Yeah, left. Okay. And we pointed to this animal and we said, give me a cat. It would give me this cat. Oh, repeat the question. If this animal were not virtual, and so there were animal on both sides here, this animal, the left animal would be the left cat and the right animal would be the right cat. It's, again, unambiguous. I'm pointing to an animal. It definitely is that cat. It will try to make me happy. All right. So this problem is actually analogous to a problem we face in the other dynamic runtime type info based thing that we do in C++, which is try catch. Right? If I throw a Siamese cat and I try to catch it as a cat, is a Siamese cat a cat? No, it's two cats. So this will actually not hit that first catch handler, but it will hit the second one because a Siamese cat is a single animal. So this raises one more question. What about this case? So here, I have a pointer to the right cat as right cat, and I say, I would like this cat, please. Which cat do I mean? Now in this case, the answer is, there is a specific cat that is more like this right cat than the other one. So yes, we do the right thing here. It tries to make us happy. And also, yes, my slide corrects me, this is not really a truly dynamic cast. In this case, right cat actually inherits from cat. So not only is the right cat a cat, but the compiler knows at compile time that a right cat is a cat. And when you point to a right cat and you say you want the cat, you obviously want the cat that's the base object of that. And it can compute that. It actually turns into a static cast, as long as it's an accessible and unambiguous base class of right cat. And if it's an inaccessible base class, you're trying to cast to a private base class and you're not a friend, then the dynamic cast is ill-formed and you get a compile time error. So this is not a truly dynamic cast, and we're going to distinguish now between things that the compiler can figure out on its own and things that really have to be done truly dynamically at runtime. All right, dynamic cast. For the Itanium spec, there are 3 truly dynamic casts. Dynamic cast to the most derived class. So I can actually get a pointer, a void pointer, to the most derived class. It has to be void star because I don't know what the most derived class is by definition. So it can't be that type star. It has to be a pointer that can point to anything. So it's going to be void star to the most derived class. And that's illustrated over there on the left, to most derived object. Dynamic cast across the hierarchy from cat to dog to a sibling base, or dynamic cast from a base to derived. Now going the other way, from derived to base, from cat to animal, that's a static cast. That's not truly dynamic. You can express it with a dynamic cast, but it will just happen at compile time. But we need a 4th one as well. And ironically, the 4th one is cast to base, but dynamically. So if I have a pointer to the most derived object, such as I got from dynamic cast to void star, and I have a pointer to the most derived object, and I want to know, is a Siamese cat a cat? Is a Siamese cat a right cat? For the purposes of catching, then I actually need to dynamically cast to a base where I have an object that I don't know, statically I don't know what it is, but dynamically I have a pointer to it. I have its address, that is, and I want to know if that is a dog. So that's the 4th truly dynamic cast. So let's implement dynamic cast to most derived class. Now don't do this at home. Or do this only at home. Don't do this at work. Dynamic cast to void star. That's literally just find me the address of the most derived object. And the address of the most derived object is just that MDO offset, the -16 there, plus the this pointer. So just load up my vputter and grab that offset and add it, and I'm done. That's like 2 instructions. Every major compiler does inline it. They generate optimal inline code. Great. Awesome. Dynamic cast to sibling base. In this case, we have a cat ref, and we're trying to convert it to a dog ref. We have a cat star, we're trying to convert it to a dog star. The compiler already knows statically that cat and dog are unrelated. Why? Because if a cat inherited from dog, then this would be a static cast, and it wouldn't be truly dynamic, and I wouldn't be trying to do it. And if dog inherited from cat, this would be the downcast that we're going to look at next. So in this case, we know that they're not related. Not all cats are dogs, not all dogs are cats. The only way for this dynamic cast to succeed is if some dogs are cats, if someone has made a cat dog by inheriting from both of them. So what this means is that if either of these classes is final, if either of them is final, then this dynamic cast must fail. It must give us null putter. the compiler knows this statically. It knows whether these two are final. And so it should give us optimal code gen, but it doesn't. Clang will optimize if the source is final, but not if the dest is final, and none of the other major compilers do. Here's how we do it, assuming they're not final. There might be a cat dog, and this might be a cat dog. In that case, what we do is we cast to the most derived class, and we ask for its type ID. That's just in its vtable. And if that's still the type ID of cat, then we haven't changed it, and we can just fail. This actually was just a cat. Otherwise, it's something else. It's something that someone else has Frankensteined together, and it might contain a dog. So in that case, I have a thing that I don't know what it is, but I have a pointer to it, and it might be a dog, and I would like to find out if it is. This is exactly the case that we have when we catch an object of polymorphic type. And we want to know, should this catch handler apply? Is this thing a dog? Should it be caught as a dog? So in that case, we want to use our cast to base, which we're going to write. But that's exactly the same operation we would do in a catch handler. So let's do that cast to base. This is where I diverge from the Itanium ABI. I say, I just want to solve the problem at hand, which is I have a pointer to a thing, and I have its vputter, I have its vtable, I have its type ID in its vtable, I have some type info about it. I have its RTTI, basically. And I would like to know if it is a dog. So I could just write a function that tells me if this thing is a dog, and just put a pointer to it in the RTTI, in the runtime type info, in the vtable somewhere. And it would look something like this. This is just sort of a list for each class of its bases, where if you name one of its bases, one of its public unambiguous bases, it just gives you a pointer to that base. Ask me for a base, and I will give it to you if I know about it. And if I don't know about it, then it's not a base of me, and so I'll give you null. This, coincidentally, is exactly the behavior I want from dynamic cast. This is also exactly the behavior I want from catch. What's the difference here? Oh, this is a happy cat dog. So it has one animal subobject. So if you ask the happy cat dog for its animal base, it will give you its animal base because it is an animal. The angry cat dog with non-virtual inheritance has two animal subobjects. So the angry cat dog is not an animal. And if you ask it for its animal subobject, it doesn't know about it. It's going to give you null in that case. All right, so let's do a quick example here. Here I have function test. It takes an animal star. It tries to convert it to a dog star dynamically. So I have a pointer to an animal. This is inside a cat dog, by the way. It happens. I don't know that yet. All I see is I see a pointer to this animal this animal object. But it's polymorphic, so it has a v pointer. And I'm trying to dynamic cast it. So step one is I get the v pointer. I go over there, and I get the offset to the most derived object, minus 40. Cool. Now I take my original animal, this pointer, and I subtract 40. And I go up there. Now I have the address of the v pointer of the most derived object. I no longer have any idea what the type of that is. I know it's the most derived type, which has somewhere within it an animal subobject, and that's all I know about it. But I know this is a v pointer, so I'm going to follow its v pointer for some polymorphic type. So I know that I can get its type info, its type ID from a known offset, or in this case, let's just pretend the function pointer is in the vtable. And I call that function with the pointer to that highlighted address, the beginning of the most derived object, and I call it with the type ID of dog, which is what I'm looking for, and I just trust that it will tell me if this thing has a dog subobject. If it doesn't, that's also nice to know. And in this case, hooray, I get it. But actually, this is not how either Itanium or MSVC do it. They don't just write this little function. They actually generate data, read-only data, that represents the entire class hierarchy. And when they want to know if one thing is another thing, they will do a graph algorithm. They will do some Dijkstra's algorithm and stuff to try to figure out if there's a path from A to B. And they get it wrong, and there are bugs. You won't run into those bugs in practice, but I will file those bugs. Is there a question?
The previous slide, this disagrees with what you said earlier as an algorithm as how we go from base to derived. But the difference here is that the base was a virtual base, and that's why it looks more similar to sibling, the sibling lookup. Like a few slides earlier, you showed us how to go from base to derived.
Yes, from base to derived.
Yeah, so this is sibling, and a bit before that was how to go from base to derived.
To most derived. The first case is going to the most derived object as void, the dynamic cast of void star. That's the easy case.
That's the easiest.
Yeah. And then what we're doing to go to sibling is we're actually simplifying that into first go to the most derived object, and then ask whether that object whose dynamic type I don't know, ask it whether it can be this type, and if so, get that.
How do you know you're going to the most derived object? You don't know beforehand.
We know that we're going to the most derived object because we know every object with polymorphic type has a most derived object, but we don't know what it is. But the fact that it has one means that we can put where it is in its vtable at a known offset, which is what we do. And that is actually what Itanium does as well.
You can never know statically on a dynamic cast, this dynamic cast is going to the most derived object, unless that most derived object happens to be finite.
You can know statically that the dynamic cast wants the most derived object because the user told you that that's what they want. They say dynamic cast of void star, or they say dynamic cast to some sibling base, which is unrelated, in which case how we do that is first we cast a void star, and then we ask that object for...
So you said Clang optimizes if the source is declared final. Does it optimize if the target is declared final? That's a problem, or missing.
It's a missing optimization. But it's one fewer missing optimization than GCC, MSVC, or ICC. And one of these days they'll fix it. It's like a one-line change. They could fix it. All right. Quick digression on accessible versus public, because I've been using both of those terms here. Here I have a sponge. A sponge is an animal, but it's not widely known that a sponge is an animal. So if I'm in a context that knows about sponges, is a friend of sponges, then static casting from sponge to animal is okay. Right? I point to a sponge, I would say, I would like this animal, and it says, all right, here, there's the animal. Now, if I'm in a context which is not a friend of sponges, and I say, I point to a sponge and say, I would like this animal, please. The compiler will say, that doesn't look like an animal. And you'll get an error, right? Because you're trying to static cast to something that looks unrelated. So both static cast and dynamic cast from derived to base require that the target base be unambiguous and accessible in the current lexical scope. And remember, dynamic cast from derived to base is really just a static cast in disguise. So it has the same requirements as static cast. But now let's try throw catch, which again goes from derived to base, right? I throw a sponge and I try to catch an animal. Here comes the sponge, catch that animal. It doesn't look like an animal. And now lexical scope doesn't matter, because at runtime there is no such thing as lexical scope. If I'm at runtime and all my lexical scopes are gone, all I have is machine code and library functions, and they don't really understand the concept of scope. Here comes a sponge, catch that animal. It would be wrong to catch it, because that would imply knowledge of the sponge-animal relationship, which not everyone has. And so all of these operations in the C++ standard are defined so that runtime knows nothing. Runtime is not your friend. Runtime is nobody's friend. Right? I throw the sponge, I attempt to catch an animal, doesn't look like an animal, I don't catch it. Doesn't matter where I am lexically. No such thing as lexical scope at runtime. All right. So that's why cast to base here, which is used by catch and which is also used by dynamic cast to a sibling base, requires that the target base be unambiguous and public, not just accessible, but public, because there is no such thing as lexical scope at runtime. All right. We are now down to the last case, which is casting from base to derived. I have a pointer to an animal, and I would like that cat, please. So again, I don't know statically, if I have an animal star, I don't know that it is a cat. So I have to do something at runtime to find out if it's a cat. And now I can't use that same trick. One reason I can't use that same trick is the Siamese cat issue. The other reason is that I might have, let's say, a coral reef, which is in this example, is a fish and is a sponge. This is a horrible, this is not Liskov substitutable at all. Please, again, don't try this at work. But let's say a coral reef has a fish and a sponge. Is a fish and a sponge. And a fish is an animal, and a sponge is an animal, but hardly anybody knows it. And now I point to this animal, and I say, I would like, wait, which one am I doing here? Yes, point to this animal and say, I would like this sponge, please. This works because this animal is a reef, and a reef is a sponge, and there's only one sponge I could possibly be talking about. Everybody knows it. We get that sponge. But if I point to this animal, the right-hand animal that is actually a sub-object of sponge, and I say, I would like this sponge, that actually doesn't work. That will give me null, because that would require the runtime to admit that this animal is a sponge. This is the animal sub-object of a sponge, but you're not supposed to know that a sponge has an animal sub-object at all. So we actually have the cast from the left-hand animal to sponge works. The cast from the right-hand animal to sponge actually doesn't work, because there's no lexical scopes, because runtime is not your friend. All right. So how are we actually going to do this? This now gets tricky, right? Because we can't use our trick anymore. I want to point that out. We can't just say, I will go to the most derived object, which is reef, and then I will ask it for its public base sponge. That would actually always give us sponge in this case, and that's not what dynamic cast wants to do. So we can't implement dynamic cast that way. We have to have a new trick to make one of these work and the other one not work. So here's what we're going to do. We're going to find the most derived object. And then, at this point, we're going to ask it two questions. We're going to ask it, is that animal subobject that we started with a public base of a sponge subobject, whether you're supposed to know about it or not? And it can tell us that. And otherwise, is that animal subobject that we started with a public base of yourself? If so, then it's okay to give me your public sponge subobject. And here's code for that. All right. And now I've explained that. I'm going a little bit fast. I thought we only have 10 minutes, but suddenly I have fewer slides than I thought. So let me go back to that slide for a minute and ask, is there any questions? Yeah.
I have a question about the Siamese cat again, the one with like this,
Right.
say, and it's not protected.
Okay.
Well, actually, not like this. Siamese cat and has two animal bases, and you want to go from animal to the derived cat. How do you know to get to the right cat?
How do you know when I'm going from an animal to a cat and a Siamese cat? How do I know which cat to go to? Because if that animal that I started with is a public base of a cat subobject, the most derived object will know that statically when we do the struct layout of the most derived object. And so it will be able to answer this question in the affirmative and say, yes, your point, I can see you're pointing to the left animal, you want the left cat. I can see you're pointing to the right animal, you want the right cat. It knows that.
That function will know the full graph layout of the most derived object.
That function will know the full graph layout of the most derived object because it is generated as part of the RTTI of that most derived type at the time we're doing the struct layout for the most derived type. It knows everything about the struct layout. Yes, it knows everything about the struct layout of that type because it's generated as the RTTI for that type. So here's a possible implementation. Again, this is not what Itanium or Visual Studio do. They actually do a whole graph. They depth first search this graph. It is slow. It is buggy. Graph algorithms are hard. And when you try to do them efficiently, they get harder. And ironically, you make more bugs. Let's put everything together and see what we've ended up with. So I wrote this template called Dynamicast. And it takes P, which here is a pointer type representing what we want to dynamic cast to, and it deduces what we've got as the argument from. It deduces from, and here 2 is the type we're casting to, and yeah, it's just remove pointer of P. So here's what dynamic cast should do. Number 1, if we're casting to the same type, just return the object. We're done. Number 2, if this is a an accessible base, accessible unambiguous base, just cast to that and we're done. And I'm using a C-style cast, which is sneaky because that can actually cast to private bases, and you can't actually check for accessibility with type traits. So even for private bases, this will just make it work. Then, if we're casting to void star, that means the user's asking for a pointer to the most derived object and they don't care what it is. So I'll just return the most derived object, and I'll show code for that in the next slide. If we're casting, we're casting we're kind of down the hierarchy from the base to a derived class. I've got some code for that. And otherwise, we have unrelated sibling classes, and we're casting between them. So first of all, here's the non-portable stuff, the stuff that you're not supposed to do at work. A truly dynamic cast to the most derived object means take the vputter. This is a pointer to a polymorphic object, which means in the Itanium ABI, the thing at that offset, that's going to be a vputter, and I can just go grab it. That's not true of MSVC. It gets a little bit more complicated. Look at my repo, which I hope is linked from one of these slides, to see how it's done in MSVC. We go grab the offset to MDO, and we add it to our this pointer, and we return our this pointer. That concludes casting to void star. We also have this function, dynamic type ID. What that does is get the type info of some polymorphic object, whose type, again, I don't know, but I know how to go into its vtable and grab that type ID out. So you can write that. Again, not at work. Truly dynamic from base to derived. I'm going to skip this, I think, because we're running out of time. Truly dynamic between unrelated classes. Here's our completed code. Looks the same as the previous code because I skipped the implementations. I want to get to the benchmark numbers. So I wrote this Python script as part of this. I was testing this, trying to make sure I could actually write dynamic cast, and so I needed to write some tests. And so I decided the right way to do that was with a fuzzer. I highly recommend this if you're doing any kind of operating on something that looks kind of like a language. Write yourself a little fuzzer. Write a test case generator. So I wrote a test case generator. It would generate 10 random classes, starting with class 1, class 2, class 3, all of which had no base classes, and then it would start putting them together in different ways. Public virtual class 1, private virtual class 2, public virtual, private, public. It would put them all together in various combinations until it got down to class 10. And then it would generate all possible dynamic casts. From class 1 star to class 10 star, from class 1 star to class 3 star, from class 3 star to class 5 star. It would generate all of them, and then it would run them. And it would make sure that the output corresponded to what I got running it through libc++ or libstd++, and that's how I found a bunch of bugs. And then as long as I had that test case generator, I wrote a benchmark, because why not? So the benchmark code looks something like this. This is the link to the GitHub with all of the code. And I ran my benchmark comparing my dynamic cast using the templates and the extremely non-portable Itanium ABI magic that we just saw. And I got these numbers out, and I said, all right, well, I didn't do any worse. But I really, maybe I'm like egotistical, but I really expected to do better. I really expected to do better than the default libc++ library implementation that's on my MacBook. Because this is all templates, it's all get inlined, it's all inlined. Right. -03, okay. Yes, that was -0. This is when you turn on optimizations. Then the green bars here are, this is basically faster, fewer milliseconds, slower, more milliseconds. The units don't matter because this is extremely munge, but faster to slower. The green bars are a histogram of my performance on these randomly generated extremely non-realistic cast from one type to the other, and that's native dynamic cast on the same data. And on the top here, that's pulled out in a separate histogram, a much less interesting histogram. That's casting the void star. And you see that we're exactly the same because compilers do generate inlined, perfectly efficient code for casting the void star. But anything where you're calling the library implementation of under dynamic cast, that library routine will not get inlined. It can't be. It will not get any more optimized based on different things, such as being final or not. So turns out I can do better. And then here's the last slide I have is a slightly more realistic benchmark where I'm only compiling my custom RTTI functions with O3 and everything else is O0. That's under the assumption that you can compile, that libc++ would be compiled with O3. And then your code, I can't really control what your code does. And there I'm doing just a little bit better. It's not as dramatic. That I think is the entire talk, and we have like 2 minutes for questions. Thank you for coming. Back there.
I'm just curious, did you look at the size of the generated binary? Because it seems like maybe with your approach, you're like generating all these functions and like hard code the answers basically. So maybe it's like a space versus speed trade-off.
So yeah, the question is, how does the size of these generated functions compare to the size in data of the RTTI data? And the answer is, I don't know. I didn't look at that. I would expect them to be roughly comparable. Notice that most of these functions, the vast majority of these functions are just return nullputter, which is like 3 bytes on x86. So.
I just want to clarify something. You said the numbers, the benchmark numbers you had were for these giant class hierarchies?
Yes.
Okay. Do you have numbers for like realistic, class hierarchies?
No. But if you have a realistic class hierarchy and you would like to try this out, I would be very interested to know realistic numbers.
First time I looked at dynamic cast, I was curious why we were spending so much time inside of string comparison. And eventually the reason I found out was that if you are capable of doing a DLL, well, the DLL can have its own class hierarchy whose base classes have to be the same as yours. Then the vtable for the base object, there can be more than one of them in memory. The only way to tell if that's the base class you're looking for is to actually compare the string associated with it. I kind of wonder if some of that isn't going on in terms of the non-optimized.
The observation was that on some platforms, dynamic cast can actually do string comparisons instead of pointer comparisons. That, like in this slide where I didn't really do this slide, but the underlying things here where it says like TI equal, and that's type ID of the 2 type. And that comparison could be a string comparison on some platforms. In general, I think in the old days, it actually used to be a string comparison more often. These days, they will at least try to compare the addresses first, and then only then fall back to string comparison. So I don't think that they would do the string comparisons in this case. You would still be paying for that extra branch, maybe. But yes. Alrighty.